Okay, perfect. Yeah. We don't need to put it here. This week it's a pleasure to have Steingasser, which is currently at MIT doing a postdoc. Before that, Thomas did his bachelor's, master's, PhD in Munich. And he's going to talk to us about the interesting, which is Higgs criticality on the metastability bound. Please.
Yes, so, yeah, hello. But just ahead, interrupt me whenever you want, whenever something's unclear. The talk is structured in such a way that I say all of the important things in the first half, and then afterwards just get into more details. So if something conceptual is not immediately clear, just tell me, and most of it is published anyway. I think really the concepts are the most important stuff here. Okay, so yeah, as the title says, and I just announced, I will talk to you about something that some people, including myself, believe could be a new paradigm for how to do fundamental physics. And why do we need one? Why can't we just do what we've been doing enough? Okay. Yeah, why the kind of old school particle physics no longer work as we would have hoped. You all may hopefully seen the Higgs potential. And if you see Higgs potential, you know that there are three parameters in the potential. We have a constant term that one could argue is related to the cosmological constant. I will not get into that. We have a mass term that is subject to the so-called hierarchy problem. And we have over here the coupling, which is related to a problem called the metastability of the electric vacuum. I will quickly summarize the problem in a second. And the striking observation is that the Higgs is one of the most fundamental parts, one of the most important parts of the Standard Model. It's coupling to everything, it's super important. And it has three parameters, and we can't really explain any of those three parameters. And what makes all of them confusing is that they can all be understood as some sort of fine-tuning problem. But then you all know, if you have to severely fine-tune your model to achieve something, like to achieve it, to make it describe reality, there's a chance that you're not really understanding what is going on. And yeah, let me quickly explain what I mean by that. So that we have our three parameters. I will not get into this one. The mass term is subject to the hierarchy problem, which is a severe problem, which comes out of the idea that the Standard Model should just be some effective description of some more fundamental theory. But and I guess we can all agree that there should be physics beyond the Standard Model. And if you believe this, that there is physics beyond the Standard Model, and you do just some generic, simple EFT computation, you will always get something of the form where the Higgs mass that comes out of your computation is some parameter in your larger model, and some corrections that come out of integrating out heavier particles, for example. And normally what would happen is, if you just assume kind of a generic nice particle physics model, is that all of these parameters should be of order of the scale of whatever the physics is. And that would then immediately imply that, but if you add two generic numbers of the same order of magnitude, their sum should also be of the same order of magnitude. Thus, LHC has been running for more than 10 years now. We found the Higgs, which probed up to 14 eV, and nothing else has been found, which means that this scale here, so the scale where whatever comes beyond the Standard Model should appear, is significantly larger than the parameter that we get out of here. And if you only think in terms of this very simple EFT logic that is admittedly very beautiful, you will see that the only way of getting this parameter to be small is if you have some cancellation between a bunch of parameters that come together to form the Higgs. And that is, of course, weird. it's confusing. That is something we don't really understand. And even if you don't care about understanding where this model comes from, you only care about building a collider and seeing things. This is also a severe problem. So far, particle physics has always progressed by basically applying this logic inward. But we thought there is some problem at the scale. We get where we should find new physics to build a bigger collider. We found a new physics. But if this kind of nice EFT logic fails, and we can have cancellations that give us kind of magically small number, it becomes basically impossible to get some sense of where new physics should be. Right? Because if I tell you I have some magical mechanism that, or I just consider it okay, can fine-tune these two parameters to get the Higgs mass 10 orders of magnitude lighter than the next particle, I could also do 100, 1,000, doesn't matter. So that is, and that then of course really touches the predictability of any model that we have. And that's a very severe problem of any particle physics model building, and we should address this. And I have an idea how. Okay. Then the next equally puzzling feature of the Higgs potential is if you go to very high energies and just set the Higgs mass from very small, so you can forget about it. What you have is just this nice vortex down here. And what you can also do is, because we understand the Standard Model with measure coupling, we can see what this potential looks like at high energies by taking this vortex coupling, solving the RD equation. And you find this, if you do it, you will find this extremely striking behavior that all of the couplings appear also, in a sense, fine-tuned to let this vortex coupling run down to 0 and then hover around at a pretty small negative value, and then eventually behind the Planck scale come back out. Now, the coupling changing a sign in itself is not super confusing, but what makes it so interesting is that if you think about the consequences that it has for the potential, because potential is lambda h24, if lambda becomes negative, potential flips over, potential becomes unbounded from below, and we can tunnel from the electric vacuum where we're sitting now over here, which would just destroy the universe. But for all the parameters appear in a sense very fine-tuned, this can happen, but we're in a very narrow sliver of parameters where it will happen only after a very long period of time. And all of this is also super sensitive, and I have a plot that shows this. This is from a older paper that I have nothing to do with. So here you see the value of the vortex coupling that is showed you at the Planck scale for reference. Here, the Yukawa coupling of the top quark. And what did I mean by fine-tuning? By fine-tuning, I meant that if you are somewhere here in this parameter space, the quark coupling does not turn negative, the potential remains 5 to the 4, everything is nice. If you're somewhere over here, you either don't form an electric vacuum at all, or you form one, but it decays immediately. And only in this extremely narrow little area here do we have a vacuum that can decay, but lives long enough to explain the tens of years of the universe. This is a bit outdated, and right now we are even closer to this meeting point, to this point here where all the lines converge. And yeah, also that, of course, in itself is not a problem. Right? Those are the couplings, they do what they do. But it is of course something that Green here could make something going on. There might be something significant happening here, especially since we have kind of pattern that all of our parameters seem to be involved in something that looks like conspiracies achieving something that's kind of unexpected from an old school particle physics perspective. Are you all okay that these are problems? Are you concerned? Okay.
Well, the running you are doing with the particles of the standard model. So
yeah.
Why you should stay on that? You are already close to that already.
So first of all, we don't know where new particles can come in. I will talk about modifying the coupling later in a way that makes a lot of sense. But even if you assume that there are, I don't know, this is not physical, and just we were unlucky at 20 meters from new scalar, then it would also be kind of an interesting observation that by taking out this one, whatever particle you need to add, we happen to sit in this magical point. But it's only an illusion. And but as I said, I will mess with this running with it. Okay. These are the problems, these are the patterns, and how can we make sense of it? Now, let me make more clear what I tried to say in a more elaborate way. We have the Higgs potential, we have 3 parameters, all of them appear fine-tuned, and a way of interpreting, a way of maybe making sense of this would be to observe that all of these fine-tunings are fine-tunings that lead to the universe being close to doing their respective things. For example, if one wants to talk about the cosmic constant problem, which I won't, one could argue that the constant being where it is just means the universe is close to this transition from being anti-de Sitter, collapsing to de Sitter, very quickly. Right? The mass term being very small means we're very close to the transition where we have the nice Mexican head that we all know and have contained symmetry breaking to one where the mass term is positive and we have no symmetry. Similarly here, right, for the quartic, that was obvious from the last 2 panels, we are very close to the transition from nice, safe, stable vacuum to universe collapsing. And one could now, having rephrased these problems in this way, look beyond particle physics. In particular, in the field of dynamic systems theory and quantum matter, they have a concept called a quantum phase or a quantum phase. If you know thermal phase transitions, it's the same, just you change the parameter instead of the temperature. If you don't, this would be what we call quantum phases, so qualitatively different models, qualitatively different behavior that come out of varying some parameters, and those parameters marginally we call critical values, which is why I will say criticality a lot. So by criticality, I will always mean some parameter close to one of these critical values where the universe suddenly is qualitatively very different. And as I said, and you probably all, if you do particle physics, you probably are very unhappy now because this is not what particle physics should be doing. This is not what naturalness should be doing. But it is something that happens in dynamical systems. And I will now give you a very silly example before becoming.
Here's a question about the E naught that you don't want to talk about.
Yeah.
Okay. So if you naively compute that from field theory, you get something which is way of the observed cosmological constant. So what do you refer to?
Yeah. So one way of thinking about it would be to say that you do step computation that meant you get some prediction at some large scale to the power of 4, and then you just add a constant term that pretty much cancels that out almost. Yeah. Exactly. And but yeah, so clearly.
And now, which is the point that is the transition is interrupted the picture? This is after the reduction we found to the observed cosmology. And it has basically nothing to do.
That's why I'm not talking about it.
Okay.
It's a healing. I'm talking about these two. Okay. A nice pattern that emerges that one cannot take not seriously in this case, but it's a way of thinking about this. And historically, that's where people first thought about these dynamic explanations. And okay, but maybe some dynamical explanation can explain this very interesting behavior. And I will now give you a very silly example. So that's the particle physics in the real world. I was at a conference. I went with a collaborator for a walk. We were talking only about physics, obviously. And because I think too much about criticality, I observed that this pattern here seems weirdly fine-tuned. But if you look at these footsteps, and you think in purely particle physics logic, you would think, but you would be confused by why these footsteps are exactly, not exactly, but very close to this line where how far the water gets. If you just do standard natural particle physics logic, but you would expect something here, some nice order one number, but not this weirdly fine-tuned behavior. But of course, you know this is silly, some of you are laughing because you know that's not what's going on. This is actually a dynamical system. So what was happening? We had 2 degrees of freedom. One of them knew what sunscreen is and hence was fine walking in the sand. One of them was me, who does not know what sunscreen is and had to be in the water to cool down. So we had 2 degrees of freedom, which were interacting with each other, opposing forces, and then just naturally convert those to the critical trajectory here. That's silly examples. They are better ones, but they are more. They make people follow you. Okay. So, but what's the idea here? How could you formalize this a bit and also use more serious examples? We have, in a sense, two phases. But we have one where my friend's feet are dry. We have one when I am staying cold. But because these particles of freedom have an interaction, we just converge to this particular line. And therefore, if you look at more serious physical systems, it's something that in a similar manner we'll find many times. And just to clarify some language, so in a sense, the criticality can act as an attractor, as a dynamic attractor. And this phenomenon is normally called self-organized criticality. But we start with a system that is normal, has generic initial conditions, but because of how the dynamics unfold, it converges to something that looks special. And as I said before, the fact that this happens in a system now leads to this idea that maybe those Higgs parameters that appear equally unintuitive, equally fine-tuned, are the result of something that's a physics version of a mechanism like this. And because the first people to think about it had a string theory background, we call it vacuum selection. So in string theory, you have a lot of vacuum. Each vacuum corresponds to different parameters, and choosing a set of parameters is equivalent to choosing a vacuum. But when I say vacuum selection, because I say I can't help but say this, so that's how my brain works, I normally mean this. Something chooses a set of parameters or leads to a set of parameters in a way that doesn't really matter too much. Okay. Now, that's a very nice idea, but how can we relate it? How can we get predictions out of it? How can we use it for model building? One way would be to simply go ahead and build those dynamic mechanisms, which many people are doing. It's very tedious and it's very hard to do because we have very little orientation. But we know what has to come out of it, but how to do it is just very far out of reach. We might never be able to test it if it's some inflationary process or some quantum gravity compactification. We can't see that. So what we have to do is look for ways in which this pattern could manifest, which we can see, which we can test, and then hopefully from there go back to building all these mechanisms. And one simple observation that I rely on a lot is that I just showed you several ways in which the standard model potential can undergo phase transition. There is another one, which is if you were to vary the Higgs mass, you can, if you vary the Higgs mass while keeping the quartic coupling as it is, keeping that IG trajectory, you will find that you just learned about phases. There are different phases associated with the Higgs mass. But if the Higgs mass is kind of small, what you get is the behavior that you know. So here we have the minus m squared term being dominant, then lambda phi to the vortex over lambda positive, so the potential goes up. Then at some point the quartic coupling turns 0 and then negative, so the potential goes down. That is what we have if we only assume the standard model. But you could now imagine, hypothetically, you vary the Higgs the mass parameter, you make it larger, and then eventually what will happen is that you still come out of 0 in this regime where you have a negative Higgs mass parameter. At some point, the quartic coupling takes over, but the quartic coupling has already run to a negative value. So when the quartic takes over, still the potential is negative. So we have no electron vacuum, and the two are separated by some critical value. And if you do some very simple math, you get this. There are some numbers missing here, but the scaling that for the electroweak minimum to exist, you need to satisfy this upper bound in terms of the scale where the quartic coupling turns negative. Okay, now why is this important? Why am I talking about this particular phase condition? It seems a bit far away from the ones that I've shown. So it is because being close to the phase condition is something that many of these mechanisms, there are not so many mechanisms, but a lot of the existing mechanisms for achieving this kind of near critical behavior for the Higgs field, they all point at, not they all, but several of them point at this particular inequality.
bit confused about the graph on the right. Okay, if you say the last scenario, the blue one is m squared strongly positive, let's say, then why would it right?
This is using the time convention.
Oh, yeah, for minus in there.
Yeah.
Okay.
Okay. Not very impressed. Okay, so the point is, this is something that comes out of many of these mechanisms that people have built trying to explain fine-tuning. And to give you a quick overview, if we have time at the end, I will give you the details. One of them was built by this group at CERN at the point. They call it self-organized localization, because self-organized criticality was only taken by the dynamical systems people. And they basically get this inequality as a prediction. They produce some statistics that I'm happy to elaborate towards the end. And essentially what they get is the Higgs mass term should be very close to the bound that I just showed you. Then slightly more recent work shows that if you assume metastability of the vacuum, we just say you want the vacuum to metastable and you want to have some transmissibility breaking for any reason whatsoever. Here's one example for mechanism that can do this. Then you get this as a necessary condition for these two little assumptions here. And you also get a very large extra compression between the scale where the quartic coupling becomes negative and the scale where you would expect it. If you do supersymmetry, this would be the zoom scale. If you like composite, this would be the compositeness scale where you would expect it to be. But as I said, it's not really a theorem, but a strong argument that if you want your vacuum to be metastable and break the standard gauge group, you need to have this. Then a more recent paper also points out that you can arrive at this point by just from very general assumptions on what your landscape of vacuum should look like and some quantity. Point being, this is something that comes out a lot without people trying to find it, and usually with people trying to explain either the Higgs mass or the force. Now, why is this? We believe that this is reasonable. That some mechanisms to fit.
So how this
Yeah. So that is indeed how you get to the feeling. So we have this bound. And if you believe in only the standard model, and you want to extrapolate the standard model, with that, I didn't say it before, but if you do what he said, you run the quartic coupling, it turns 0 at 10 to the 11 GeV. And as we check this at many roots of accuracy, 10 to the 11 GeV is a lot larger than 100 GeV. So if you believe in only the standard model and you want to believe in any of the mechanisms, you can't do both at the same time. But that also suggests that if you want any of those mechanisms to work, you cannot have just the standard model. You need to have new physics, and especially you need to have new physics that changes the running in such a way that this parameter here orders of magnitude smaller. Luckily, it comes out of running, which is algorithmically, so orders of magnitude smaller is not hard to achieve. And that's basically what leads to this, why I call this a new paradigm and how you can use this model. So, as that right now, there are very few explanations for the Higgs mass for the coupling. There are some, and all of them point at this inequality. And that also implies that if you don't find any new physics that can get this parameter into a range where we get a reasonable Higgs mass, we can falsify all of those mechanisms at the same time, which is great because we should falsify things. And it, of course, allows for very rich model building and favors very specific physics. And yeah, here's a list of some examples what people try to do.
in this context, even within the standard model, what calculation of the running coupling do you rely on? Because perturbation theory, are you also including all the standard model? Or?
So this 10 to the 11, we basically took or you can take the PDG data or the parameters translated to M bar run the coupling for integration with beta functions. And I think here we did all the couplings we do, and the wrong gauge coupling. There's like one term at 40 that's very important, also included that. And that's how this number is the state of the art of the
You sure that the final on.
I mean, there are significant like error bars coming in from most of the top few colors, but even if you go to even if you scan the entire 95% error ellipsoid, confidence ellipsoid, this number will be somewhere between 10 to the 9 and 10 to the 19 dB. But it's going to be a very high energy. That's the point. Like you can't get it lower with just this. Okay. And yeah, so for a reason that will become clear later, I will mostly focus. There are two of these realizations that are more recent that have a lot of theoretical advantages. I will explain the impact on this particular model, and we call it the complete model, clear, and show you how to basically turn the need for this inequality to be satisfied into predictions for a concrete model which can be tested. Okay, now what's the general idea? Let's say you find this feeling you want to implement it in the model, and you have given up on relying on natural. So, as I said, if you want any of these mechanisms, and any mechanisms people will build in the future that lead to this inequality, to explain the Higgs mass, you need to lower the scale to I, but that will inevitably also lower the lifetime hierarchy. But if you remember before the plot with the little sliver in the middle, it's easy to see if you do something drastic to your coupling, you can very easily get into a regime where the vacuum is just super unstable. And in particular, if you want to do this in such a way that you get your instability scale down, which you need to extend the Higgs mass, the lifetime of the vacuum will just be a lot shorter than the universe, than the age of the universe. And we know the age of the universe. We see it. We can take this as observational input. So all of this only really works out if you have a very distinct pattern of physics, where you have essentially the Higgs mass, then some new fermion pops up, drives the quantity down, and then some new boson appears. Which again is a very distinct and concrete pattern that you need for any of these mechanisms with pheno, and also very easy to falsify. With that, if you go to if you build FPC, you find new fermion, we killed off all of these models. But if you do, then that's but if we find something that follows this pattern, that would be, of course, no proof that any of this makes sense, but then it would be a very nice, that would be a very nice smoking gun, as the Americans call it. Okay. And I will argue that in the next generation of colliders, we can basically test for this one model, very difficult analogy. All of this is in range of next generation colliders. And hence, this is a good thing, but an interesting thing to implement when you do model building. Okay. Just a few open questions that some of you may have had or will have after I point them out. So this is all of them are addressed by the model that we're using, otherwise I would not show them. So this is a very specific ordering space. It makes sense from a pheno perspective, but obviously that is something that might require some justification for us to rectify when you model. Then, of course, computing the lifetime of the vacuum for any model is generically a very hard task, especially if you have extra bosons involved. And you may also ask the question, I said before, that the Higgs mass bound comes out of the existence of the instability scale. But why does the quartic have to turn? That's not necessarily, but you could think of other ways in which you can build a metastable vacuum. You just keep the quartic positive, you introduce higher dimensional operators, and that will generate other minimums. And yeah, those are these are other open questions in addition to all the pheno parts. And I will now show you a very concrete model where we recently published a full analysis of that model under all of the premises, and will show you that all of this makes sense, it's inevitable and testable. And the model that we use, we being me and these collaborators of mine, is the measurable model. What is the measurable model? The measurable model, we take the Higgs, we add right-handed neutrinos. The right-handed neutrinos are a fermion. They lower the instability space. And we have very strong reasons to believe that they exist. Right? So neutrinos have a mass. Type 1 T4 is the simplest way of giving them a mass. So it's a more or less conservative assumption that right-handed neutrinos. No crazy speculation there. And what the measurable model does is, instead of just adding a mass term by hand for the right-handed neutrino, that mass term comes out of the coupling to some additional Higgs. And the first thing that it immediately achieves is that the masses of the scalar and the right-handed neutrino, fermions, because they're set by the same depth, they are naturally very close to each other. Naturally, not meaning in terms of naturalness, but small number, they're roughly at the same stage. And so, how can we then proceed? The next thing we need to be able to do, if we want to constrain our parameter space,
Arbitrary coupling involved.
yes, but they will
Coupling can be of any magnitude.
Yes, but the point is that if you want to believe in Bitcoin, all of this requires you to have very distinct values for those couplings. They will all be in a very small range, and in the end, I have collider projections. But yeah, of course, this could be any number, but unless you want to add extra fine tuning, it makes sense to have these scales to each other.
Or you can always make many different layers.
In a sense, this is really, we were trying to implement all of these assumptions and answer all of the questions with the smallest amount of adding numbers by hand or making additional assumptions. Cool. Okay, then another cool thing is that we know the potential of the model, and this allows us to do two things. The first one, it allows us to literally brute force plot all the qualitative ways this potential can look like, for all its quantum spaces, and search for configurations in which we can satisfy these two assumptions that I mentioned before, so metastable vacuum mixes and less contained symmetry breaking. And the magic of it is that if you look at just the tree-level potential, it doesn't work. You cannot have it. But as we know in the standard model, metastability comes out of the running of the vortex. And if you do a very simple analysis that is in the paper where we do this, you will find that there is indeed one configuration which in the UV can be described by this potential here. But then when you go to the IR, include the running of the coupling, you get a mesh with a vacuum. That has contained symmetry breaking, so everything makes sense. It also explains why we need the metastability to arrive from the running of the quarter coupling. Otherwise, there is no vacuum. And a nice little technical side note, because we know the potential, we can calculate tunneling rate, so we can check if a set of parameters that we find existing does allow the vacuum to live for long enough. And that will later on give us some major constraints. Okay. And here are the constraints. So the first thing we checked is we looked at the right-handed neutrinos, the Yukawa coupling, and checked, basically scanned how strong our Higgs mass bond would be. So here we have the mass of our right-handed neutrinos. Here we have the Yukawa coupling, meaning the trace of their matrix. And the different colors here correspond to a different mass on the different bound on the Higgs mass. And here, that's the most interesting part. That's where the bound is smaller than 10 eV. Two little footnotes. One of them, as I said, this is the simplest possible toy model. We've worked with other models since then. Yeah, this bound is around 700 eV. And you should not be close to the bound. So if you remember the plot I showed you in the beginning, the bound means there is no potential barrier protecting the vacuum. But if the bound is saturated, wave your hand, the vacuum indicates. So you need to have some barrier whose height no one can quantify at this point. This is a lot of hard computation. But you need to have a barrier, which means that you have to be below this very over-identified. So right now, we kind of guess based on how much knowledge we have about all these catalyzed current processes, getting this bound to be 10 eV is probably where we will come out if we when we eventually know how to do all these computations. But also think of it as a proof of concept. So probably this is okay if you don't believe that our estimates there are okay. We can do better with different models. I think that's true. And the more interesting part here, if you care about this entire region here is included in the FTP range. So in these FTP could, okay, if this makes sense, if we have the marginal model as if any of these mechanisms that I mentioned before or something similar is realized in nature, we have to find, and you believe in the marginal model, you have to find resonant neutrinos. If you run FTP and you find absolutely nothing, then this is probably there. Here, in terms of the mixing angle, or the mixing angle of the power coupling, yeah, that's very nice FTP range, and not yet excluded by LH. Now, then the other component that we have is the scalar field, and that's where our ability to compute vacuum lifetimes is important. As I said before, more generally, having these large power couplings will destabilize the vacuum, very much so. That means we need a very strong stabilizing effect, which means that the effect of the scalar to stabilize the vacuum also has to be large. And what connects those two, and the way in, right? So let's just looking at the potential, it is kind of easy to see that the two scalars talk to each other through this orbital coupling. So if you want the effect of the extra scalar on the Higgs vacuum to be significant, this coupling should be somewhat large, and you don't want the scale to be too large, otherwise you get some 1/m squared suppression and things don't work out. And then by a nice series of coincidences, we did not have engineered it. What you get is that here we have, so this is the interesting part of parameter space, the yellow one. That's where the vacuum lives longer than 10 to 10 years. If we were down here, the vacuum would have died already. Up here, we are getting non-perturbative. So we are really only left with this very small little yellow triangle here in our scalar parameter space. And that happens to also give a very strong signal for FTCH8. You get the stabilization comes out of this dimension 6 term here. We know the sensitivity of FTCH8 for this dimension 6 term. And you see it's completely in here. Now, you could point out that I chose some reporting of the scalar here in a certain way. And we can also vary that one. And you see that unless you make this other coupling also very small, you generally have a very nice coverage, but of course not 100%. So if for some reason you insist that the quartic coupling of the other scalars should be small, there are some little spots that FTCH8 should be. But overall, we have a very nice coverage. Plus, as I said, this would only be interesting for the timeline for future colliders, as it would be built first. So if we see any of those fermions, we know that the scalar has to be there. And even if it's sitting somewhere here and we don't see it, we know it has to exist. So in a sense, we already have to do an observation. But of course, if you want a target for FTCH, this would be a good one, and especially that we find one of those neutrinos, we know it has to be there.
Okay, large alpha, you don't like it because it becomes non-perturbative, you don't know how to compute it.
Yeah. Yeah, it's just, we don't know what's happening up here.
You're right.
Yeah.
Okay.
I mean, maybe someone else. Yeah. Also, it's hard to cut a plot along the fermion line. Okay. But yeah, so far that's the modular model. And just to give you the general idea, but if you don't like this particular model, take it as a proof of concept, take it as a way in which, if you have a model that you like and you want to see if it is consistent with any of those approaches to solving the hierarchy problem, what you need is let's say you believe in this inequality, or you want to predict this inequality, you want to quantify this inequality, you need to lower this parameter here, and as you do it, make sure that you don't mistake the vacuum too much, which in our case here was graphene and neutrinos, and an additional scalar, which probably can be both found in future slides. Okay. Are there questions? No?
We can wait.
Okay, you can wait. Okay.
Did you make a similar model with Iraq?
Depends on how they affect the running of the code. If you add more quarks, of course, that will affect the running of the code.
Would it be possible, or you have to check?
We checked with generic vector like fermions, not really thinking about whether they even have to recharge, but naively, because the top quark is driving the running down, I would think that that should work. If you want vector like quark, they can probably do it. And then, of course, you have to worry about destabilizing, but at least following the stability scale, good. Okay. Good. Then, some examples. I kept saying all those mechanisms that achieve this inequality. Under the assumption that I convinced that this is actually interesting and we can test it, and I'm not doing anything too obscure. Let me show you some of these examples. It's definitely an incomplete set. People only started doing this a few years ago. I assume many more models can be built to lead to this one inequality, which are therefore tested. But just to give you a sense of what people have tried. So here is the first model that I mentioned by the group of firm. They tried to be extremely conservative, very minimalistic in their approach. So they took the Higgs potential and basically just added a new scalar, which they gave very specific properties, which might not be generic. But what matters here is the idea is basically you have your parameters, both with a new scalar. The values of those parameters depend on what the additional scalar is going to be. And then they did something very funny. They assumed some probability distribution for the value of the scalar in the early universe for inflation. Then they let inflation run. And what happens? And they showed it by solving the Fokker-Planck equation. It's a very long and hard to read paper, but to summarize it, they start from some generic probability distribution for the scalar field, and it all the way Fokker-Planck equation works in inflation, it becomes naturally localized, and they end up with a very strongly localized probability distribution at the end of inflation, where if you, for example, if you sample the quarter coupling, it will come out relatively close to where you have this inequality realized. Okay, then another mechanism, or not really mechanism, but argument that is in this recent paper with my collaborators. Something that we observed, we're trying to play with scanning over parameters and trying to build more concrete models, is that, as I said before, the existence of the electron vacuum is very much sensitive, or very much depends on the fact that the Higgs mass is tuned to be very small. So if you start from a kind of generic landscape, if you just assume your parameters can take certain values, but don't let them take any values, and don't talk too much about, or don't get too much into probability distributions, you can make the simple observation that this second minimum down here, we added something to protect the vacuum from being unloaded from below. The existence of this vacuum and the properties of this vacuum are not super sensitive to how you, for example, vary the mass parameter. But you could think of some landscape where you just vary the mass parameter. As you vary it, you will always, not always, but in almost all the cases, find this vacuum exists and its energy varies only very little as the massive mass parameter. Whereas the existence of this area up here is very sensitive. Now, what is the assumption that goes into this? Or not really assumption, but the observation. The observation is that in the case of Standard Model, the energy of the vacuum is extremely negative. But even if you assume that the instability scale is like 10 TeV or something, the energy here will be something like, let's say, minus 100 TeV to the power of 4. Cosmological constant is a lot smaller than that. So unless but if you take this observation as given, that this vacuum here, these properties are not quite sensitive to how you vary your parameters during some scanning, is very negative, you can get, so you can arrive at a very simple assumption of observation, really, that generically, if you don't have fine-tuned parameters, you don't fine-tune your mark, you will get a potential, but because you don't have the barrier up here, your Higgs field will just roll down, you part of the phase branches, and you think in terms of, for example, eternal inflation, that only those patches where you end up falling into a vacuum where the Higgs mass parameter is small enough to make this barrier, only those survive. So if you want to constrain what your parameters can do, you naturally fall into this vacuum here in those crunches. If you have fine tuning, you make the barrier, that universe has a chance of not crunching away in it. And the last one is we're getting more creative, but also getting very interesting. So this paper here and several follow-ups did something very different. As you saw the last two, that was kind of very close to particle physics. We add some scalar fields and do some cosmological arguments. What these guys did is to just go on other level of abstraction, acknowledge that all we kind of want, everything we wanted to assume is you have different values. You have different sets of parameters, and they then decided to model those as a network. So, not all of these methods come from dynamical systems, so they wanted to use some of those. So they modeled the landscape as a network where vacuum decay or tunneling processes correspond to link. What you can imagine, you start here, the vacuum is unstable, you tunnel into different vacuum, then you find yourself here, and so on and so on. And what you can then do is, if you have this network, you can do some very much not particle physics computations for probability for statistics on this kind of network. And what you will find is that a certain topology of the network is preferred, which, if you translate everything back to particle physics, means you have a metastable vacuum. And then, as I said, there is this quote-unquote theorem or very strong argument that if you also want to have metastability breaking, you end up with this pattern here. Okay, so I think it's only 10 minutes left. I can either explain you this little theorem here, or show you an argument why we don't actually need to assume things. What do you? Okay, then I will go. Perfect. Okay, so what is the theorem that I mentioned? As I said, this is the most general argument we could find, or okay, one of the most agnostic approaches for how to arrive at this inequality that I keep throwing at you every 5 seconds, which is that if you want the vacuum to be metastable and want the metastability breaking, you need to have a small system. How do you get it? This first part here, that's kind of evident, but the electric vacuum does not exist if this is not satisfied. But now, how can we relate this instability scale to the scale to the natural Higgs? Again, natural Higgs not thinking in terms of you embed the Higgs in some number framework, supersymmetry, composite. Anything you heard of as a solution to the hierarchy problem would fall into this category. And what you can then do is do a perturbative computation where you first look at only the standard model running. And what you will find is that at high energy, with lambda phi to the 4, so everything is classically invariant. When you do the tunneling computation, I don't know how many of you care about instantons, but if you do, you will find that Euclidean action that suppresses the tunneling rate is 1 over the absolute value of the coupling, where the scale at which you evaluate the quartic coupling is basically the scale where the quartic coupling reaches its minimum. Right? You can easily see that. So it's classically scale invariant, which means you have not one instrument with many of them, but for each of them you have, because each of them corresponds to different RD scales in here. So what you can do is you can integrate over all of them, and you can either perform the integral, which is tedious, or just use a saddle point approximation, minimize the exponent, so you minimize the expression, so you end up with that instanton being dominant where the quartic coupling is the smallest. And that with just the standard model, but of course with that we don't care about only the standard model. We want to explain why this scale is smaller than the natural. We want to connect it to the natural value of sigma in some theory where we embed the now, because we want to remain more or less analytical, what we can do is instead of using the full supersymmetric composite, whatever model you like, we can add a dimension 6 term. So that's going to be the dominant contribution from the CSM physics. We can afterwards check that it is a good expression. Now, then, just by dimension analysis, what you get is, of course, standard model plus you have a dimension 6 term, so something over lambda squared. The only other scale we have is the scale associated with the instanton. So you get this little correction here. And then what happens is the two leading order, you still keep your one parameter family of instantons. You still integrate over them. You can still do the saddle point approximation, which means you try to extremize this exponent here. And extremizing this exponent means you take the derivative and set it to 0. And now what do we have? We have 1 over a coupling and the dimension over here. And once you realize that you have this structure, two things happen. So this coupling here runs only the derivative here. So this guy is loop suppressed. Here we have a nice quadratic dependence. So you can, without doing algebra, or you can get here, you can also do the algebra, that the contribution of this term here to the derivative can be a lot larger than the contribution coming from here, even though the term itself, when it comes to the impact on the action, is subdominant. Simply because taking the derivative gives you an extra big factor here. And right, you can now again look what you can see what this term does is mu squared. So it's the smallest is mu small. So you get this interesting behavior where basically this term here drives the scale at which you evaluate your instanton to smaller scale very efficiently. The term here in front tries to push it to the minimum, and you end up with some intermediate scale. And yeah, what that does is the timing rate is e to the minus quartic coupling at this intermediate scale. And if you now want to assume any lifetime, so you have some mechanism that predicts a lifetime, like the one I just showed you, that will predict a lifetime. That translates to a value of the quartic coupling at this intermediate scale. But we know that this intermediate scale is exponentially smaller than the scale where we have the dimension 6 operator. And what this then basically tells you is the quartic coupling has to take a certain negative value at this intermediate scale based on whatever argument you want to give for the metastatic vacuum. You get a few extra orders of magnitude where supersymmetry, compositeness, whatever you want. Yes. If one of you does something that's not compositeness or supersymmetry, please tell me. I keep committing that. Okay.
Question: you're doing here some impact on gas or liquid or something? Or
no, we just compute the tunneling.
About focusing on chemical solution.
Yes. Okay. Single instanton approximation, because if you want the lifetime to be very, very long, all this are like GeV arguments. We're talking about a lifetime of 10 to the 10 years, which on those scales is just an enormous lifetime, which translates to an enormous depression. So back tunneling multi-instrument effect, all that is super super. And yes, now the last point I would like to make is here we have assumed spontaneous symmetry breaking, but I always implicitly assume the mass term to be negative. I will say it now as I'm about to solve that. And yeah, more recently, me and two collaborators found a reason why we don't need spontaneous symmetry breaking. And if you are entirely thinking in terms of scanning your conditions, that is actually a very significant assumption. Because let's say you have here the range of Higgs masses that make sense coming from the theory. It could have the minus n squared, but we could also have the plus n. And the argument I just showed you more or less excludes a big chunk over here, but doesn't say anything about what's happening over here. So if you think purely statistically, you could think that this is not very useful. It's only tells us that there is no spontaneous symmetry. So what we did is we considered that, and the collaborators.
Oh, yeah, that's last.
Exactly. Yeah. So I want to show why the plus sign is also constrained and can be constrained more. So before the argument of if you have a minus sign, what happens if the mass becomes too small is that the electroweak vacuum then disappears, but it keeps the lower line. However, if you put a plus sign here and an h squared, which is nothing, you can do a similar analysis and you find that, and by the way, the mass of this is that if you make the mass term large enough, nothing really changes for the percentage out here. But as you get to larger values of the Higgs field, at some point your mass term becomes so large that the minimum that you would otherwise form by the quadratic coupling turn negative disappears. And now again, this is not a metastability bound. So if you believe in one of these selection mechanisms or want to test one of these selection mechanisms that needs to go metastability vacuum, this takes up here to the student, this one is defined. And there is some very simple math you can do, but it ends up giving you a bound on the Higgs mass, which, if you remember before, it was 1 beta lambda, mu I squared, and an additional hierarchy. So this scales differently. And why is it nice that it scales differently? Because it allows us to do the following. We can put next to each other these two blocks here. So this would be the bound that we get on the Higgs mass with some assumptions on the running of the quartic, we had some fermions. By now you understand how to do that. And then compare for each set of for each set of fermion parameters, how strong the bound gets. This is not super intuitive, so we can overlay them. And we get, first of all, here a combined. If you don't want to assume the mass, you assume the mass could be anything. What you should do is really to get the bound on the observed Higgs mass, overlay the two, because either of the two could be true.
Where is the?
Here we just use vector like just a good point. Yeah. The simplest thing we could. And what we found here was, okay, again, also if you move beyond this considering the minus m squared case, but also allow for plus m squared parameters, a very nice coverage of pretty much all of the interesting range where we get a bound here by FTP. And the conceptually interesting point that I was rushing towards to is this one. So here we have plotted the ratio of the two bounds. So how strong is the bound on the positive mass parameter versus how strong is the bound on the negative mass parameter. And the interesting part is really here in this regime where we get a Higgs bound or a bound on the Higgs mass that is small, that is really in a regime where you're comfortable to hope that this might explain the hierarchy problem. That's where this here is right. That means, and plus the bound on the positive mass parameter is smaller, or it's more stringent than on the negative. So if you don't want to assume spontaneous multiplicity, you don't want to assume anything, and you really just hit this with a flat prior, you don't want to assume anything, you will find that exactly in that regime, where you get a strong bound on the Higgs mass, the bound that you would get as no spontaneous integrating would be stronger, means that more of the allowed parameters, spontaneous integrating is more common than not having spontaneous integrating in this very narrow regime where we're able to explain this with any of the, by just assuming metastability, which comes out of some mechanism. Okay, that is everything I need.
We come up with this anyone, and we have time to speak. So I can start. What exactly do you mean by classically thin invariant?
The potential is lambda phi to the 4. There is no scale.
Okay.
And the three level everything.
The scale will be conformal invariant. Or not?
No, I mean, there is, like you mean, there is, you have a lambda phi to the 4th view, so there is no scale in that potential.
Okay.
Classically. But of course, the running then changes things, but that's.
The running changes and then.
That's what fixes the scale.
Okay. And then when you have your network thingy,
do
you have any assumptions on how the network has to be connected or something?
Yes. Several. So the assumptions were you don't back tunnel, so you only can go to lower lying minima.
Okay.
Which is very plausible, but not necessary. And of course, if you're dealing with a large network, you have to specify a probability measure. And the probability measure that they specify a probability measure, which is basically, you assume you can randomly drop an observer in one of the minima. They call it the observer measure. And then they can follow that observer on its world line throughout the evolution. And then most of that world line in a way that they quantify, which is of course based on assumptions, because the matter problem exists, will be in the tool. In this tunnel where you have a vacuum, which is metastable, in this case, has a lifetime of 10 to the 130 years.
And that at what point in the early universe it would happen? Because at some point you could have back.
No. So this is not on the scale of when, but this is when you. So you have inflation, you populate the universe. At some point, the universe dies by vacuum decay, and then you pop over here. You again have inflation, reheating, all the things. You kind of live out your life in the universe. At some point, that one dies by vacuum decay. So it's really kind of on the scale of many inflation cycles.
And then I have. So when you have your thingy going down like that, and they all end up in like a well, right? You have some kind of behavior like 6.9, 6.63 because they don't matter. It doesn't matter which initial values you have. You're always going to end up in this kind of minimum. Not here, not further down, or further back. I can't remember. We have
which thingy?
Where you have, you say you vary with your parameters, and you're always going to end up in this. Or there.
Yes.
Yes. You have some kind of limitation loop running to a 6 point or 6 line or something?
No, we literally just assume the running of the quadratic coupling. We play it, you vary a bit, you vary the couplings a bit, you vary the mass parameter a bit, you vary the dimension 6 term that we added here to keep the potential from being unbounded from below. And that's really the only thing to vary.
That's right, but you always end up in the same, so you run into the same, you're always running, start with different points and you always run into the same. region.
I mean, the same region. Because if you imagine, you have like, let's say you have like minus lambda 5 to the 4 plus some 5 to the 6, then the energy of this minimum will always be like minus some number coupling to the 4.
Okay.
The lambda to the 4.
And can you relate that to, again, early universe phase transition or something?
We didn't go that far.
You didn't go that far. If you did in your Majoron model, could you relate the math of the Majoron to electroweak phase transition because you have it related to some phase transition because you have related to metastability at the end?
Maybe. Well, so because the Majoron, literally the state of the art is what I showed you. So those projections we're currently got to the scalar is not actually the Majoron, it's the radial mode of the complex singlet. Complex SC2 singlet. So yeah, we're currently, Belen and I are currently doing the Majoron maths and see how that affects things. But
if you have that, you could even try to see if you have a signaling threshold or some characteristics for your phase transition. You could have even a signaling gravitational wave, or you could act something like that to put as an extra constraint.
That's one of the things we're trying. That's where we're going.
Okay.
It's
very nice.
Very new.
Oh, very nice. More questions?
In order to get the conclusion or scale it with for something about 0, and then restabilize that.
Yeah.
You need to couple the things to fermions to be stabilized, and then couple the things to bosons to be stabilized. How generic is each of these? For example, do other particles, can you use other particles to destabilize the vacuum? Use beyond fermions and use other particles beyond bosons to destabilize? Like how generic is the method?
Okay, so for destabilizing, let's start that because it's more constrained. In principle, I mean, the beta functions are they're very complicated and nonlinear, but to get this extremely strong effect, you need something to come in as running order. So something like minus y, like minus you cover to the 4. And the only thing I noticed changes the running in such an effect in such a way at this order without a lot of explicit question is extra-fermion. There's another paper more recently from some people we're also working with. They use an ALP, but they use a threshold correction. So you can just manually kick the quartic down a bit and then don't change the running. But for the running itself,
so what would be different in this matter?
So the right. So it's okay. So basically, what they do is they say there is an ALP that does not affect the running because it's a scalar, it's not running too much. But by kind of backwards integrating out the ALP, you find that the coupling is actually not 0.1, but somewhere down here. And then, of course, even if you're running slowly as you're doing the standard model, you still reach 0 fast. So in the permeabilizations, we start from what we get from the standard model, run down faster, they add this one correction, and then they also get to 0 quicker. But yeah, that's for the fermion. Or the boson. Okay, scalar, do a very good job. We use the scalar here because Belen likes to have this coincidence of scales. You would also have a gauge boson, anything. Okay, now the gauge boson scalar fermion.
Yeah.
More questions? More questions? So thank you very much, Mark, for this review.
And we check
Yeah, exactly.
So, my name is Jaime Badi. I was here. Another work is I will start with